Hey guys, welcome to part 1 of problem set 3, the atom. We'll start with number 1. Fill in the missing information about the atoms of the 4 nuclides in the following table. Okay, I've written carbon 12 like this, but you'll probably see it written like this in the form A, Z, X, like that, where this is the mass number, so I'll just put A here and then Z here for the proton count, okay? This is just the letter for the element that we're using on the periodic table. All right, so if I look at carbon, you're going to want to use the periodic table to fill out this chart. It's going to be pretty much the only resource that you need here. Now, if you look, on the left-hand corner is always going to be your Z count. Okay, that's going to be your Z count. Okay, Z. And that's just the number of protons, okay? So that's 6. Now, we're working with carbon 12. 12, the mass number is the sum of the protons and the neutrons, okay? So if I know that there's 12 total and there's 6 protons, then there must be 6 neutrons. And they told me the mass number just by giving me this, so this is 12, right? So this number plus this number should always equal that. And it's a neutral atom. Neutral meaning there's no charge on it, okay? There's no charge on it. They didn't tell me, otherwise it's not an ion, okay? So it's going to be 6 electrons as well to balance out the positive charge on the protons, okay? Protons are positively charged, electrons are negatively charged. They have to be the same in order to give you a neutral atom, okay? All right, on to the next one. Okay, 35, okay? What element has 35 in the top left-hand corner? It looks like it's bromine, okay? And they tell me that the number of neutrons is 46, so this must be the 81 isotope, okay, if I add those together. And it must be the same number of electrons, given that this is neutral, so this is going to be the bromine 81, right? Next one. So number of electrons, we're assuming that these are going to be the same because we're not charged here, so this is going to be 37 here. 37. What element has 37 up here? It looks like it's rubidium. Okay, rubidium. And this is going to be the rubidium 85 isotope. And all I have to do is take 35 minus 37 to get the number of neutrons. And if I do that, I get 48, right? 48. All right, last one. What element has 92 at the top left-hand corner? Looks like it's uranium. Okay, uranium, and they already give me the mass number, so it's uranium-235. Okay, remember, these can also be written like this. Okay, same... either format is actually just as valid in for chemistry terms. All right, 235, and then I'm going to assume that it's neutral, so 92 electrons, and 235 minus 92 is 143 neutrons. Okay. All right, the second table here is going to be a little different because we're working with ions. Ions are charged particles, whether they be positive or negative. And that just means we have an imbalance of protons to electrons or vice versa, okay? That means we can have an excess of electrons or a deficiency in electrons, and that will determine whether or not this thing is charged, how this thing is charged. All right, so remember this silver atom can also be written as such, like that, okay? That just means, so that means if I look at the periodic table for proton count, right, I know that any silver atom has 47 protons. Okay, and I can't assume that that's the same number of electrons because this thing is charged, but I do know that it's positively charged, so there's 1 extra proton. So that means there must be 46 electrons. Okay, does that make sense? They tell me the mass number here is 108, right? Just given right there. So number of neutrons is just 108 minus 47, not 46. 108 minus 47 because we want to take away the protons, and that would give me 61 neutrons. All right, number of protons. What element has 9 protons? Fluorine. Okay, if we look at the periodic table, top left-hand corner, 9 for fluorine. Mass number is 19, so this may be fluorine 19. 19 minus 9 is 10 neutrons. And it looks like I have 1 extra electron than I do protons, so this is going to be 1 minus. Okay, 1 minus. All right, next one. Let's see, the number of electrons here they give us, we can't just use that to determine the number of protons, right? We're an ion, so we can't say that this is going to be exactly the same. So the next one that you want to look at is the mass number. Okay, what element has a mass number closest to 16? And if you look, it looks like it's oxygen. Okay, oxygen, I'm going to put oxygen 16. And let's just assume that and see if we can confirm that. So if I have 8 neutrons, that would mean, yep, I have 8 protons. So yeah, that totally works. And it looks like I have two extra electrons than I do protons, right? So this is going to be the 2 minus ion. Okay, last one. What element has 80 protons? And if we look at the periodic table, it looks like it's mercury. And if I just add these together to get the mass number, I get 201. So that's going to be the mercury 201 isotope. And it's charged, right? I've got too few electrons, or 2 less electrons. So that's going to be a 2 plus ion. Okay? All right. What is an isotope? Isotope is so atoms that have that are the same element from. I'll just put same from the same element. From same element, meaning what? Meaning they have the same number of protons. Same number of protons. Okay, but different number of neutrons. Different number of neutrons. Okay. So, for example, we've got the 79 bromine isotope and we've got the 81 bromine isotope. They're the same element, right? It's still the same number of protons. It's just that each one has. It turns out that this one has 2 extra neutrons, right? 2 extra neutrons. All right, part B. Explain the inherent redundancy in the nuclide symbol AZX, okay, or just AZX like this. Okay, we were using the proton count, remember, to identify the element. So this is actually really redundant. We're just if I notice that I've written this bromine isotope as just the 79, right? Because I already know that because it's bromine, it has 35 protons, and I don't need to write that there. I could technically say bromine and then 35 down here. It's just saying the same thing, right? So we just leave that out just for simplicity's sake. Okay. Letter C. Write the symbol of the most abundant isotope of nitrogen. How many neutrons does it have? To do this, all you have to do is look on the periodic table and look at the mass number. That would be this one right there. The atomic weight is what we call it. So if I look at nitrogens, it looks like it's 14.007, and this would be, the units here are actually grams per mole. Okay. That means the most abundant isotope is 99% of the time, it's going to be the one closest to this value. So I would say the 14 nitrogen isotope. Okay. And nitrogen has 7 protons, right? There'd be 7 down here. So that must mean it has 7 neutrons if I subtract those. All right. So that's how you want to look at that. Most abundant will most likely be the one that's closest to this value, right? For oxygen, we assumed that it was the 16. For oxygen, the most abundant is 16 because the atomic weight is something like 15.999, right? So that must be the most abundant isotope. Okay, and we'll talk about abundance here in a little bit as we do numbers 5 and 6. All right, number 3. A certain near-deflated balloon has a helium-4 with a total mass of 200 atomic mass units. That's what this is called, atomic mass units. Okay, and 1 AMU is equal to 1 proton or 1 neutron. Okay, they weigh about the same. Technically, neutrons are a little heavier, but when we're using atomic mass units, it could represent either a proton or a neutron. Okay, it does not represent an electron. Protons and neutrons are about 10,000 times heavier than electrons. Okay, so and then it says how many protons, electrons, and neutrons are present in the balloon. Okay, so we've got the helium-4 isotope. Okay, I know that for every helium atom, looks like, okay, so we've got a total of 4 atomic mass units. So that must be, there's 2 protons because that's what the Z is. And then 2 neutrons. And they didn't tell us it was charged, right? So that must be 2 electrons. So there's an easy way to do this and a complicated way to do this. I'm going to show you the easy way. So 200 atomic mass units. Cool. Of what? Of helium-4. Helium-4. And I know that there are 4 atomic mass units for every 1 helium-4 atom. Okay, helium-4 atom. Correct? Okay, so if I were to divide this over just like this, I would find out how many atoms I have, right? And in this case, it looks like there would be 50 atoms, 50 helium-4 atoms. But they're not looking for atoms, right? They're actually looking for number of protons, electrons, and neutrons, and there's the same number of each in every helium atom. So I'm just going to say, let's say 1 helium atom, 1 helium-4 atom. Let's just look for protons, and this will be the same number for neutrons and electrons. Okay, so see how I did this dimensional analysis? I started out with the measured value, said, okay, I know that there's 4 AMU for every 1 helium-4 atom, and then in 1 helium-4 atom there are 2 protons. Okay, so I'm going to divide these over. That's 1/2. Okay, and then 1/2 times 200. That's going to be 100 atomic mass units. So that means AMU. Sorry, protons. 100 protons, because that's the unit I ended up with here. So 100 protons, and I know that there were 2 neutrons and 2 electrons. So I could do the math again, but let's just assume because that's simpler. Okay, so 100 neutrons and 100 electrons. Okay, so that's how we do a problem like this. There's a little bit more of a complicated way that I didn't show you. It's turning AMU into grams, and there's a unit conversion for that. So you'd have to go 2 AMU times, this would be something like 1.66 times 10 to the negative 24 grams, I think. Something to that effect. It's a little more exact than what I have here, is 1 AMU. And then use the atomic weight on the periodic table, the 4.00 grams, per 1 mole of helium-4, and then go from moles to what we call Avogadro's number. So 1 mole of helium-4 to 6.022 times 10 to the 23 helium-4 atoms. Okay, and so this number here is like it's like just a number. If you say I have a mole of something, that means you have 6.022 times 10 to the 23 of that thing. Could be M&Ms, could be eggs, could be cats, something like that. Okay, it's like saying a dozen. If you say a dozen, you automatically think of the number 12, right? It doesn't. You could have a dozen of whatever you want, right? This is just a number. That's all it is. And we call it Avogadro's number. And we know that there's that many atoms of helium in 1 mole of helium, and that there are 4 grams in 1 mole of helium, and so on and so forth, going back to atomic mass units. And then you would just say, okay, I know that 1 helium-4 atom has, let's say, 2 protons, right? So this would be the more complicated way to do it. You multiply everything on the top divided by everything on the bottom, and you'd get the same answer, right? But this was a lot simpler. In fact, you probably didn't even need a calculator for the way that we did it. Okay? All right, on to number 4. How many neutrons are in 100 grams of bromine 81? All right, so here's our starting value. Let's say there's a decimal here just to say that we'll say that there's exactly 100 grams, and that'll give us 3 sig figs, okay? So let's say 81 bromine. Okay, I know that there should be 81 grams, right? That's a weight of bromine 81 for every 1 mole of 81 bromine. Okay, so that's the unit conversion that you kind of want to use there. And I'm not looking for moles of bromine, right? But if I stopped here, I would find out moles of bromine. But I don't need moles. I need neutrons, right? So let's go to atoms then next. So I would say, okay, 1 mole of 81 bromine has 6.022 times 10 to the 23 81 bromine atoms. Okay, atoms. So that the mole here will only ever tell me number of atoms. Okay, so I'm going to say cancel out my grams here, cancel out the moles here. Now somehow I must have atom next, right? So I'm just going to put 81 bromine next, atom. So I know that 81 bromine atom has what? How many neutrons does 1 atom of bromine 81 have? Well, if I look at 81 bromine, I know that there's 35, it's a 35 down there, right? So that must mean that this is 46 neutrons. Okay, and notice that this cancels too, and I end up with the unit that I need on the top. So this is how you do dimensional analysis. Start out with your measured value. Okay, I knew that I needed to turn grams into moles because moles is the only way I can get to subatomic particle counts, right? Whether that's number of atoms, number of protons, number of electrons, whatever it is, I have to first turn this number, this mass number, into moles. And we use this value, so 81 is the atomic weight of that thing in grams per mole. That's what that means, okay? On the periodic table, when we take into account all the abundances of all the different isotopes, we get this value, right? It's not going to be an exact value. You'll see 12.107 for nitrogen, right? It was 14.007. For bromine, actually, I'm pretty sure if you add up the abundance isotopes there, it's something like 79.904. In this case, we were only working with the 81 isotopes, so we didn't have like a mixture of isotopes, so we just did 81 grams instead of this value, okay? So I turn it to moles, turn it from moles to atoms, okay? Because I can only go find out how many neutrons there are by knowing how many atoms of bromine there were first, and then turn that atom into neutrons, okay? Into neutrons, and then multiply everything on the top and divide it by everything on the bottom. If you do that correctly, you get some value like 3.42 times, using sig figs, times 10 to the 25th neutrons. Okay, so that's how we do that. All right, part B is pretty similar. Okay, it's just a number of neutrons found in this many milligrams of uranium-238. Okay, same idea. Let's start with our measured value. I'm going to turn this into grams by dividing it by 1,000. So we'd say 0.00125 grams of what? 238 uranium. And then I know that there are 238 grams in 1 mole of 238 uranium. Okay? So if I stopped here, I would have moles of 238 uranium. But I don't need moles. I need neutrons. So I'm going to go to atoms next. Okay, so I know that 1 mole of 238 uranium has 6.022. Remember this number, Avogadro's number. Times 10 to the 23 atoms of 238 uranium, okay? So if I stopped here, okay, I can cancel these units out. I would get atoms of uranium-238, okay? I could find out how many atoms there are, but I don't need atoms. I need neutrons, and I know that for every 1 atom 238 uranium atom, I could find out how many neutrons there are, right? Neutrons. So there's two, let's see, the 238 isotope, I know that the proton count is 92. So 238 minus 92, that looks like it's 146, so 146 neutrons. Okay? So this is the dimensional analysis kind of thinking that you need to be able to do to solve a problem like this. Go from grams to moles. When we're working with elements, you're always going to want to turn it into moles, okay? Because the only way that we work from mass into number of particles, subatomic particles, we have to go through the mole count, and that would be the grams per mole. And this is what you find in the periodic table, or if it's an isotope, you'll just use the number that they give you, okay? That's the weight of this thing. And then just multiply everything on the top right here and divide it by everything on the bottom here. If you do it correctly using sig figs, you should get 4.62 times 10 to the 20th neutrons. All right, cool. So that will finish part 1 of problem set 3. Go ahead and go on to part 2 for problems 5 through 9.